Welcome our 12th standard students. Today we are going to discuss about force between two long parallel current carrying conductors. We know the concept of magnetic induction due to a infinite long current carrying conductor, as well as force on a current carrying conductor when it is placed in a magnetic field. Magnetic Lorentz force may going to experience. These two concepts are going to use to find the force between two long parallel current carrying conductor. What are that two concepts we are going to use means magnetic induction due to a infinite long conductors based on either V.SELVAKUMAR law or Ampere circuit law. We can find magnetic induction at a certain distance from a infinite long conductors. That concept and force on a current carrying conductor when it is placed in a magnetic field. These two are going to use to find the force between two parallel current carrying conductors. For that, we are going to take a diagram. In the diagram, two long current carrying conductors we are going to take. That may consider very long. Very long means we will take that is infinite long. So any conductors are going to take. Conductor 1, conductor 2. It may be called as a wire 1, wire 2, whatever may be there. A conductor, B conductor. The two conductors are separated certain distance. Thus, the distance can be taken as R distance. And through A conductor and B conductor, we are going to pass a current in the same directions. That is, upward direction current. First, A conductors current can be considered as I1. Second conductor, B conductor. Through that B conductor, we are passing a current I2. The two conductors are placed parallel and separated R distance. Through that, I1 and I2 current passes in the same direction. We are going to represent the direction with the help of three-dimensional Cartesian coordinate axis. So there we are drawing an axis. This is a x-axis, this is a y-axis, and z-axis. We consider upward positive z-axis towards the right y-axis. Outward direction, we have that x-axis. If outward is a positive x-axis means inward direction is a negative x-axis direction. We want to know very clear that along x-axis direction can be taken in a I cap. Along y-axis direction is a j cap. Then along that z-axis k cap. If we taken along that negative x-axis means minus I cap. Negative y-axis minus j cap. Negative, that is a negative z direction minus k cap. Anyway, now we are going to apply the direction for current as well as the current carrying conductor producing magnetic field. Based on that, we will find the direction of that force on a current carrying conductors. Anyhow, suppose now I am going to take on this first A conductor. Through that, I have passed I1 ampere current. You don't want to consider this conductor. This conductor alone we are going to take now. Based on that current through that conductor A, around the current carrying conductor, magnetic field is produced. At the R distance, the magnetic field. We know already the concept. Around the current carrying conductor, concentric circular magnetic field is produced. Concentric circular magnetic field is produced. So here at a r distance, suppose is the r distance, we draw that circle. If the conductor is in a plane, perpendicular to the plane, we are drawing a circle. Anyhow, according to the right hand thumb rule, we will find the direction of the magnetic field at this point. Direction of the magnetic field at this point. If you take on your right hand, fingers are holding, thumb only extended. The extended thumb shows the direction of the current, holding finger shows the direction of the magnetic field. So if you apply upward current at this point, inward direction magnetic field. This is the first conductor, that's why V1 magnetic field produced in inward direction. What symbol we want to use for mentioning that inward direction means cross with circle. Anyhow, this conductor produce a magnetic field at the r distance on that B conductor. Otherwise, we can take an due to this conductor producing magnetic field at r distance, either based on that V.SELVAKUMAR law or Ampere circuit law, we will write that equation. That is, magnetic field due to conductor A at r distance, according to V.SELVAKUMAR law, we can take on that equation B1. It is a vector quantity, that's why B1 vector equal to mu naught I1 by 2 pi. Distance is r, that's why 2 pi r. Then we have a direction. So that also want to mention in our right direction of our equation. So what direction it is acting? That is to that plane, inward direction. The outward axis is a positive x-axis. So that's why inward axis is negative x-axis. That's why we are mentioning minus I cap. This is a magnetic field, both magnitude and the direction, at a r distance point from the first current carrying conductor. At this place, we are going to place second current carrying conductor. That the current carrying conductors are infinite long. That's why in a B current carrying conductor, DL length is going to taken. On that DL length, this B1 magnetic field through the DL length of that second current carrying conductor, we are passing a I2 current. DL length in a B conductor, we are passing a I2 current. On that magnetic field, B1 is going to act. According to our magnetic Lorentz force, we can express that force on that current carrying conductor, that is the second current carrying conductor with a DL length. There we have a formula for that. F vector equal to, that is a vector quantity. We have a vector expression for that magnetic Lorentz force. IDL, that is second current, that's why we are mentioning I2 DL vector. Cross the acting magnetic field is a second magnetic field. That's why that can be taken as B1 vector. Then this is going to express in its values that is F vector is equal to I2 dl. That dl length in our diagram acting that positive z direction. That's why dl into k cap, positive z direction, cross. We know that b1 vector can be taken as mu naught I1 divided by 2 pi r into minus I cap. We are going to take on vectors one side, that remaining factors are taken here. That is F vector is equal to minus is taken here. Then we have taken mu naught I1 I2 dl divided by 2 pi r into k cap cross I cap. According to our cross product function, k cap cross I cap can be taken as a j cap. That's why F vector is equal to minus mu naught I1 I2 dl by 2 pi r into, instead of j cap cross I cap, that is k cap cross I cap, we can take that is j cap. This negative sign is going to taken in. That's why F vector is equal to mu naught I1 I2 dl divided by 2 pi r into minus j cap. Then for this second conductor, force per unit length. How we are going to express means, this dl is going to divide F vector divided by dl equal to mu naught I1 I2 divided by 2 pi r into minus j cap. So this is a minus j cap. Based on that Fleming's left hand rule also, we can sense the direction of the force. Otherwise, based on that cross product of that vector also we can sense. Towards that conductor A, the force on that conductor B is acting. That is, force on the conductor B is acting towards conductor A. Because of that conductor B experiences a force towards that A based on that negative y axis. That is the direction of that force on that second current carrying conductor. Similarly, on that first current carrying conductor, simultaneously, on the first current carrying conductor, second current carrying conductor's magnetic field is going to act. So that's why first conductor also going to experience the force that we are going to calculate. So that's why there we consider for r distance I2 current in conductor B. Conductor B produce a magnetic field. That magnetic field can be taken as B2, that is vector quantity. B2 vector equal to mu naught, that is second conductor's current is I2, mu naught I2 divided by 2 pi r. There we have a direction of that second magnetic field also. Based on that right hand thumb rule, we are going to express the direction of the B2 magnetic field in outward direction. Outward direction is nothing but taken as dot with a circle. To that outward direction, which direction we are going to tackle means, we already expressed that Cartesian three-dimensional coordinate axis, outward axis is taken as a positive x-axis. That's why plus I cap. So that's why B2 vector is equal to mu naught I2 divided by 2 pi r. That direction is a plus I cap. This B2 magnetic field is going to act on that first conductor. Through it current flow is I1 current. Because of its infinite length, in that we are taken a small length dl length. On that dl length, conductor A, B2 extracts a force, extract a force by B2 on that dl length conductor A. Through that I1 current is flowing. The B2 extract a force. Okay, that's all. That force can be given by magnetic Lorentz force formula. So here also we can take an F vector is equal to I, that is on that first conductor, I1 dl vector cross the magnetic field is B2 vector. Then you substitute F vector is equal to I1 into dl. What direction that is a current is acting? Upward direction the current is acting. Upward axis is z axis. That can be taken as a k cap. Then cross already B2 vector we have mu naught I2 by 2 pi r into plus I cap. So finally we can take an force per unit length. That the force per unit length can be taken as F vector dot dl. So F vector divided by dl equal to that mu naught I1 I2 divided by 2 pi r. That is force per unit length on that first conductor can be taken as F vector divided by dl equal to mu naught I1 I2 divided by 2 pi r. Then we have a vector directions k cap cross, that is k cap cross I cap. The k cap cross I cap is nothing but j cap. So from that we can take an force per unit length on that first conductor can be taken as mu naught I1 I2 divided by 2 pi r, and that is along that j cap. That along the j cap is nothing but first conductor experienced a force per unit length towards the second conductor. Similar manner, second conductor also going to experience a force towards that first conductor. That's why the forces on each conductors are going to act towards other conductors. That's why there the force are two forces are attractive forces. Forces are attractive forces. If through that two parallel current carrying conductor pass a same direction current flow, there the force is attractive force. Suppose I am going to change current in one of the conductor. What happens that the force directions as well as whether it is attractive or repel, we are going to discuss now. Okay. We know that if current through that conductors are in same direction, the forces are attractive force. We will take on this diagram. A conductor through that I1 ampere, then B conductor through that I2 ampere, placed R distance. Okay, this current carrying conductor produce a magnetic field at this point inward, plane inward, B1 magnetic field. The current in this conductor is upward, but the force acting this direction. Same time, the second conductor also produce a magnetic field on that first conductor, that is outward magnetic field, that is B2 magnetic field. Through this conductor, I1 ampere current can be experienced the force towards the second conductor, that is here. That's why if current through both the conductors are in same directions, both are going to experience a force. The two forces are attractive forces. Two forces are attractive forces. Then we have another special case. Suppose if you change the current in one of the conductor. For that we are going to take a diagram. First two conductors named as A and B. First conductor current flow is this, I1. Then their distance are R. Through that second conductor, current flow is downward direction, that is I2. Now, this conductor is going to produce a magnetic field at this point. That the magnetic field is inward direction. But current is downward direction. Based on the Fleming's left hand rule also we can change the direction of the force. In a left hand, first three fingers are going to taken. Four fingers shows the direction of the magnetic field. Mid finger shows the direction of the current. Then thumb shows the direction of the force. So anyway, here current is the downward direction. Magnetic field is inward direction. So we have that current direction is a downward direction, inward magnetic field. There experience a force in outward directions here. Then on that first conductor, the second conductor produce a magnetic field. What happened that direction of that magnetic field that can be find based on that right hand thumb rule. If you take on thumb rule, that extended thumb shows the direction of the current, folding fingers shows the direction of the magnetic field. Here, this right hand thumb rule is going to apply for that second conductor. So we have that current is downward direction. In the that is for that B conductor, right side outward magnetic field, but that A conductor is in the left side. That's why here also magnetic field B2 also inwards, current in upward direction. So what about that direction of that force? We can find either in a vector form or by the Fleming's left hand rule. Now I am applying Fleming's left hand rule. So here four fingers shows the direction of the magnetic field, mid finger shows the direction of the current, then thumb shows the direction of the force. For that, in that inward magnetic field, upward current. Inward magnetic field, upward current. Then that force is outward. So the two forces are acting outwards means the two can experience a repulsive force. The two can experience a repulsive force. So that's why from that two diagrams, if current is in the same direction through the two parallel current carrying conductors, the two can experience their force, attractive force. If the current is in opposite direction, the two can experience a repulsive force. Repulsive force. Anyway, we are going to take on the magnitude of that force between two parallel current carrying conductors. That can be taken F is equal to generally mu naught I1 I2 L divided by 2 pi r. Then force per unit length. That is F by L equal to mu naught I1 I2 divided by 2 pi r can be expressed. Now why we are going to take on this equation means based on that value substitution in our equation we will given that definition of unit of current. What is the unit of current? Ampere. The ampere, 1 ampere means when we get a 1 ampere, that values we are going to see. For that we are going to take on force per unit length equal to mu naught I1 I2 divided by 2 pi r. Suppose the two conductors are placed in air. Through that current we are passing I1 and I2. If that two are equal, I1 equal to I2 equal to suppose particular 1 ampere, their distance are also 1 meter. If you substitute this value r equal to 1 meter, I1 and I2 are equal to 1 ampere, what about that force per unit length we are going to see? That is F by L equal to, we know that mu naught is a factor called as a permeability of free space or air or vacuum that has a certain value. What value means? Mu naught contains 4 pi into 10 to the power minus 7 into, we take on that I1 and I2 values are 1 into 1. Then distance also 1 meter, that is 2 pi into 1. Your substituting are over, that is pi and pi cancel, and here we have simplified that F by L is equal to 2 into 10 to the power minus 7. We have the unit for this, that is a Newton per meter, because we express the ton as a force per unit length. Force per unit length is equal to 2 into 10 to the power minus 7 Newton per meter. If through the two conductors current is 1 ampere, that two conductors are placed 1 meter apart in air or vacuum, if that experience the force is 2 into 10 to the power minus 7 Newton per unit length. That is going to given a definition reversely. If the two conductors are experience a force when they are placed 1 meter apart in air or vacuum, the two are infinitely long conductors, then there through the conductor is current is 1 ampere. That's why definition of 1 ampere for 1 ampere. How we can take on that definition means 1 ampere is defined as that is particular current. That current can be taken as that current, that particular current, that current one ampere is defined as that current when it is passed through each of the conductors. Now the conductors are taken infinitely long, parallel straight conductors. That are kept at the distance of 1 meter apart in vacuum, 1 meter apart in vacuum. At the time, that can be causes that can be causes the each conductor to experience the force per unit length of 2 into 10 to the power minus 7 Newton per meter of the long conductors. That is the definition for 1 ampere. 1 ampere is defined as the current. Okay, 1 ampere is defined as that current when it is passed through each of that infinite long parallel straight conductors kept at a distance of 1 meter apart in vacuum causes each conductor to experience a force per unit length of 2 into 10 to the power minus 7 Newton per meter of that long conductor. This is the definition for 1 ampere. 1 ampere is defined as that current when it is passed through each of that infinite long parallel straight conductors kept at a distance of 1 meter apart in vacuum causes each conductor to experience a force per unit length of 2 into 10 to the power minus 7 Newton per meter. Based on that derivation we can get. We have completed that force between two parallel current carrying conductors. There we have a general formula is force per unit length between the two parallel current carrying conductors is equal to mu naught I1 I2 divided by 2 pi r, their magnitude. Based on that vector or Fleming's vector rule, we will give the direction of that forces. If current through that both the conductors are same direction, the two are attractive. Opposite direction current flow, that may makes a repulse. Thank you to all.